And before that, just to recap, this is your MOS transistor. Now, although MOS transistor we have looked at as a 3-terminal device, by construction the MOSFET has a 4th terminal. Hopefully you guys remembered, this is called as the body terminal or bulk terminal or substrate for NMOS, substrate terminal. You can call it either terms. So if I call this, let us say gate, drain, source, we call this the bulk or the body. I will not go into the details because you might learn it in solid state devices or other equivalent courses. And one thing to have in mind is in most processes, all the NMOS transistors share the same body terminal. So typically the body terminal is connected to the lowest potential in the circuit. Why, you might learn in other courses. I don't want to cover it here. And for NMOS it is connected to the ground. So a body terminal for all the NMOS transistors in this course will connect it to ground. Sorry? Yeah, I'm coming there, right? So for PMOS, again you have the body terminal. For a PMOS terminal, it turns out the body terminal is local to each transistor, unlike an NMOS where all NMOS share the same body. For a PMOS, each transistor will have independent control. So in principle you can connect it to anything. And the common thing is to short it to the source, because one of the implications of this 4th terminal is that the threshold voltage of the transistor changes with the source to bulk voltage. Which one? Source of these two. Yeah, you can't do it because, like I told, all the NMOS terminals have the same body. So which means if you short this, which means you are saying that you are inherently saying that source terminal of all the NMOS transistors in your circuit are also connected. For example, you might have a case like this, right? Let's say one NMOS transistor, you will have it like this. Other NMOS transistor, let us say you connect it to current source like this. Okay. So what I'm saying is the substrate terminal for all the NMOS is tied together. Okay. So which means if you short this, it means you are inherently shorting these two also. So never mind. Just remember that for NMOS transistor, you don't have independent control on where to connect the body terminal. You connect it to the lowest potential, which is ground. For the PMOS transistor, you can connect it anywhere you want, and usually you connect it to the source terminal, because in both NMOS and the PMOS, the threshold voltage is a strong function of the source to bulk voltage. So in general, if the source to bulk voltage is 0, the threshold voltage remains same or remains fine. If this voltage changes, threshold voltage also changes. So you try to keep this to be 0. So you do this. No, it is not about the VTH. Like I told, right? All the NMOS transistors, you might learn in the solid state devices course, by construction they will share the same body terminal. Okay. So which means this is basically connected. Yeah, exactly. But the point is, this is connected to the lowest terminal. Okay. Now, if you, what do you want to do? You can do, definitely. Correct. It will be different for both. Yes. Whether it's a feature or a bug, it depends on you. Right? Like, what you pointed to is absolutely correct. Now, let us say I have one NMOS transistor connected like this, other NMOS transistor connected to ground. So the substrate or the bulk is connected to ground. So for this transistor, the source to bulk voltage is 0. Whereas for this transistor, left side transistor, it is a non-zero voltage. So threshold voltage of this will be different than the threshold voltage of this. So now it's up to you whether you want to use it as a feature or say that this is not something you want, but this will happen. Okay. Yeah, so the point I wanted to make here is the following. As I already mentioned, you have parasitic capacitors between each two terminals of the MOSFET. So which means from gate to drain you have a capacitor, gate to source you have, from drain to bulk you have, source to bulk you have, everywhere. Okay. So the thing to have in mind is the gate to source capacitance is typically the dominant capacitance. That is, CGS is typically greater than CGD, CDB, which is the drain to bulk, CSB, source to bulk, etc. Okay. Cool. So this information is sufficient for transistor for now. Any questions on this? Yeah. Gate to bulk is also there. Yeah, I mean, like I told, I cannot draw everything, right? It becomes messy. See, between any two terminals, there is a capacitance. You can't prevent it. Okay. So all possible combinations on gate, source, drain, bulk you can think of, and it will have. Okay. So now let's look at the pole zeros in our circuits. So let's start with a common drain. That's simple. So let me sketch a common drain. So let us say this is where I apply the input. So I apply the input at the gate. This is small signal ground. Where will I take the output from? Source terminal. And ideally you want to put a current source here. And I'll implement the current source using an NMOS transistor. This is a small signal equivalent. So let us say M1, M2. So now let's start marking the capacitors. So from the gate, again as I told, I have capacitance from each terminal, from the gate to all terminals. What I'll do, I'll lump all the capacitors from the gate to the ground as one single capacitor. Call it as some C. So this capacitor will include the gate to drain capacitance, gate to the bulk is grounded, by the way I'm not showing it. So the gate to the bulk capacitance, and I think that's all. So similarly I have a capacitance from gate to source, let me call that C1. Right. Similarly at the output I have capacitor, I will call it C2. This will include the drain to bulk capacitance of M2. It will include the drain to gate capacitance of M2, source to bulk capacitance of M1, and you can look at it and write. Right? I'm hoping that's not difficult. Just look at the terminal and then you write it. So I lump all the capacitors and call it as C2. Right? So I'm hoping by looking at the circuit you will be able to tell what all capacitors contribute to C2. Right? From this node you find, we have gate connected, so drain to gate. Similarly the drain to substrate, drain to bulk, source to bulk of this, blah blah blah. Okay, and this is my output. So now tell me, I have an ideal voltage source and this capacitor C is in parallel to this voltage source. So do you think this capacitor is relevant? No, because it is in parallel to an ideal voltage source, so I can take it off. So I just have two capacitors, so let's look at poles and zeros. So let's start with zeros. So first let's find if we have zeros and how many zeros we can have. So as usual, the same test. What will I do? I'll short, let's say start by shorting one capacitor. If I short C2, my output is, so this is not fine, but I can short C1 and the output is non-zero. So which means I have 1 0 for sure. Can I have 2 zeros? Can I have 2 zeros here? The moment I short C1 and C2, the output is 0. So how many zeros I have? That we'll be able to say by inspection. Okay, let's also understand the origin of the 0, physical origin of 0. As I already told, we have zeros in a circuit if the output is obtained as sum of two different voltages, or I have two different currents flowing from the input to the output. Here is the output obtained as sum of two voltages, but do I have two different currents flowing from the input to the output? What are the currents? Yeah, one is through the MOSFET, other is through the capacitor. These two will have different dependence on the complex frequency S, so it can add up to 0. Now we can find the location of 0. How will I find the location of 0? I mean, at 0 frequency, what can I say about V out? So I'll assume V out of S is 0, and then I'll simply apply KCL in the circuit and solve for it. This is the only node in the circuit, correct? So let's apply KCL here. So I have currents flowing through these two fellows. Sum of these two must be equal to the currents flowing in these two. So what can you say about the currents flowing in M2 and C2? V out of S is 0. What can you say about the current here? What can you say about the current here? So I'll just look at the currents in these two branches. What is the small signal current flowing through M1? GM1 times V in of S. And what can you say about R0 of M1? Do you think that is relevant or not relevant? Why? Yeah, R0 is connected between drain, which is small signal ground, and the source, that is also assumed to be ground. So R0 will not contribute to anything. So this is the current through M1. What is the current through C1? V in of S times, this should be equal to 0. I very well know my V in of S is non-zero. So this should mean that the complex frequency S must take the value minus GM1 by C. In calculation of 0 is plain old solving the circuit using KCL, but here you know that one of the voltages is 0. So this is no longer the unknown to you. So you replace this unknown with the complex frequency S. So okay, so this is 0. So let's look at poles. Again, remember, pole location does not depend on the input or the output. So I can as well assume that the input is 0. Now, if I make input 0, what can you say about C2 and C1? I have C2 here, C1 here. How are they connected? Parallel. So I can say this is C2 plus C1. Now, what is the order of the system here? First order, I just have one capacitor. So I can directly write the pole location as 1 by the capacitance times the resistance it sees. What is the total capacitance I have? C1 plus C2 times the equivalent resistance. So let's look at the resistance. So what is the equivalent resistance looking here? Looking down, what is the resistance? Looking into the drain of M2, that is R0 of M2. Looking into the source of M1 here, yeah, that is 1 by GM1 because the drain is shorted. Fine. So my R equivalent is basically R02 in parallel with 1 by GM1. How can I approximate this as? This is approximately 1 by G. That's all. So which means the pole is roughly GM1 by C1 plus C2. Right?